Hello everyone, welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube, and you can find the link on our website. This week, we have Chard, a research assistant professor at the University of Chicago, to talk about funcX, a federated function serving fabric for science. Kyle, thank you very much for coming.
Thank you, Michelle. Thank you, everyone. Thank you for inviting me to your webinar series. I think this is my second time presenting in this webinar series. And the focus of today's talk is going to be on adapting the increasingly common function as a service model to science with what we're calling funcX. The idea being here that we're presenting a federated function as a service model. And this is the work of many people from the University of Chicago, from Argonne, and from the University of Illinois. So I guess before I get started, I thought I would include a quick slide outlining serverless computing and this whole function as a service model that is becoming increasingly popular in the cloud and in industry. And the idea behind serverless computing is essentially that we've had this adoption of cloud where people increasingly rely on virtualized resources that are run by cloud providers. Serverless basically takes that model and takes it one step further, where the cloud provider is not only abstracting the physical infrastructure, the actual hardware that sits in the data center, but they're also abstracting the virtual infrastructure, the virtual machines and containers that actually underlie the pieces of code you're executing. So in a function as a service model, essentially it's as simple as you pick a runtime. You say you want to run a function as Python. You write your function code, just a typical snippet of Python code. And then you can run that function 1 or 1,000,000 times without needing to worry at all about the actual resources that underlie the execution of that function. So essentially the cloud provider is managing all of that for you. And so what's really great about this, one, it's very easy to use. Two, it's very low latency, so you can run these things very quickly. It's on demand and elastically scales, and it can be quite cost effective if you're running just these very small snippets of code for very short periods of time. And then we're increasingly starting to see people actually combine these granular functions into larger applications or workflows to solve more complex problems. And I should say as well, please feel free to yell out if you've got questions as we go. So why do we think it's useful to adapt this model to science? So the first sort of motivating factor from our perspective is that the decomposition of applications into smaller component functions can actually be advantageous in terms of the types of use cases you can address. It can simplify the development and maintenance process. It can make it easier and more modular to be able to join these little bits together in different ways to actually achieve whatever your goal might be in terms of an application. And in terms of new use cases that it enables, it makes it easier to address like real-time and interactive stream processing type workflows or workloads, because you can basically elastically scale these very granular pieces depending on the work that you have at a particular time. The second reason we think it's really useful is that I think it's long been a challenge for scientific users and computer scientists as well to actually use the high performance and increasingly heterogeneous computing infrastructure we have available. So at the moment, I'm sure many of you are aware of the challenges of using a particular cluster there in Brazil, or a cluster here in the United States, which has typically its own type of scheduler. It has sort of strange configuration to that scheduler. You have to understand how all the policies work in terms of the queues and things like that. So typically there's a fairly high barrier for scientists to jump on board using these large HPC infrastructures. And the third thing that we think is sort of useful about this FAS model, function as a service model, is that it enables execution to be more fluid. So as we move to this world in which we have more heterogeneous computing infrastructure, it's increasingly likely that a given application, different parts of that application are going to run better in on different compute resources, and they may be different compute resources within the same computing facility, or they might be different resources that are geographically distributed. And so for this reason, we started developing this funcX system, which we're calling a high performance and federated function as a service model. So before I get into the details of what funcX is, I thought I'd dig a little bit deeper into some of those challenges that I outlined there. And so when we start thinking about workloads becoming more granular, this is a quick illustration of some of the workloads we're working with primarily at Argonne National Lab here. And the graph at the top is showing the frequency of runtimes for different functions for each of these applications. So on the leftmost graph, we see tabular file extraction. So this is a model that's basically launching a bunch of little metadata extraction functions to try and extract meaningful metadata, or in this case, tables from files. And so you see here, the runtimes are on the order of fractions of seconds. Things like machine learning models, the MNIST digit prediction model, inference here is running for maybe a second or two. Dial stills processing is a crystallography processing analysis pipeline. Tomography is another, it's an APS beamline application, all the way through to spectroscopy, where you're seeing that these types of applications, the individual functions that are doing the work of that application are actually all taking less than a minute. And so if you think about developing infrastructure to support these types of applications, if you've got to think about provisioning nodes on an HPC resource, configuring those nodes, or provisioning cloud virtual machines, the actual overhead of configuring that infrastructure can be much, much greater than the actual runtime of the individual components of the application. As I said before, the existing computational infrastructure in the scientific world is typically difficult to use. There's these complex queuing systems that have unpredictable delays. I think we're all probably well accustomed to submitting a job and not knowing if it's going to run today or 7 days from now. The allocation model for these machines is very coarse. So when we talk about using, say, supercomputers at Argonne, if you want to run something for a day on the Theta supercomputer, you've got to provision many, many hundreds of nodes. And that doesn't necessarily jive well with the types of workloads that we just talked about, where we might have, say, thousands of very short duration functions that arrive at 1 minute, and then we've got some time before we need to then run the next set of little functions. And then the biggest problem, I think, is that there's this very high learning curve and there's a lack of portability. And again, I think this community understands this well. It's quite hard to take a code that works on one machine and move it to another machine, not only because of the different schedulers, but because of the different architectures, because of the different modules, different versions of code, and even down to the different container technology that exists. So here in the United States, if we move between, say, NERSC and Argonne, we've got two different types of containers, Singularity and Shifter, that we have to use. So the takeaway point there is there's a fairly significant impedance mismatch between the types of workloads I talked about 2 slides ago and the type of infrastructure we have available that's commonly used by the science community. And I alluded to this earlier as well, that we're seeing this increasing heterogeneity of system architecture. And as we start developing more specialized architectures where we have TPUs, GPUs, more specialized types of accelerators for particular types of applications, then we're increasingly seeing this need to actually distribute our codes. It's not feasible for a single computing center to be both optimized for, say, CPU workloads and also optimized for, say, tensor-based workloads. And so what we're seeing as we near the end of Moore's law, we're seeing more specialization to try and eke the most performance out of our hardware. And what we're establishing is what people call a computing continuum, where the capacity of computing devices really, it flows in terms of a continuum from very specialized devices that are very fast for particular things through to very large-scale general computing devices that might not be as optimized, but they have much larger capacity. And so, as I said before, that this increasing specialization leads to distribution. And so we basically need to be able to send compute tasks to different places to be able to optimally run them. And so an example here of the benefits of this need to be able to move computation around, this idea of computational fluidity, being able to move compute tasks to different places, is well illustrated by this application we've seen here at Fermilab. And the idea here is that these researchers are performing high energy physics calculations where they're trying to tag and analyze neutrino events. And so their compute task on CPUs that they have at Fermilab, roughly each task runs for about 2 seconds. And you'd say that's pretty good. That's a fairly efficient piece of code that's running very quickly to do some processing. But the interesting thing is if we actually are able to run that same piece of code on an FPGA, we can run it in a fraction of the time. We can run that same piece of code in 30 milliseconds. Of course, at Fermilab, we have lots of CPUs available. We don't have lots of FPGAs available, but cloud providers such as Amazon are providing FPGA computing resources, where essentially these researchers now face this trade-off. Is it better for them to take their compute task and run it locally where it's going to run for 2 seconds, or is it better for them to ship that compute task over to Virginia or wherever the the data center is that Amazon's running and run it in a fraction of the time. And the takeaway here is that even if we add in the cost of actually transferring that function and potentially some of the data that goes with it across to Virginia, here from Chicago, Fermilabs in Chicago, we're still seeing a close to 40 times acceleration by being able to do this. And when you start to think about the fact that an application has lots of these different components that might need to be routed, say Fermilab has great CPU resources, Argonne has great GPU resources, we can start shipping things to GPUs at Argonne, we can start shipping things to FPGAs on Amazon or elsewhere. Of course, you're probably sitting back saying this doesn't sound particularly new. Remote execution's something we've been talking about since, I don't know, at least 50 years, probably longer. And so this whole motivation of remote computing, I think the same types of things that we've talked about for many decades still apply here. We want to really compute where it makes the most sense, where there are specialized resources available, where our data might live, where we think our analysis is going to compute fastest, where the queues are empty, where there's a particular software license available, etc. Why do we think that now we have an opportunity to actually sort of move the needle a little bit here? And the reason is that there's some available technology now that wasn't available a couple of decades ago that make this a lot easier. So the first is that high-speed networks are fairly pervasive now, so we can easily ship large amounts of data around the world in very short amounts of time. The second is that we have these very nice web-based authentication authorization models, these universal trust fabrics, by which we can do granular authentication and delegation. And the third is that containers have become increasingly powerful and well supported in most of the compute environments that we deal with. So this whole virtualization model has become more lightweight and more universally supported and adopted. So that brings us to funcX, which is the system we've developed at the moment. We've just received NSF funding a couple of months to make it real. We've got a prototype of the system that's being used in several use cases that I'll get to towards the end. So the idea of this funcX system is that it's sort of there's two pieces to it. There's a cloud-hosted service that allows users to basically register functions, and then they can use that cloud-hosted service to send that function for execution on a remote endpoint. So the second piece is this remote endpoint software, which sits on a computing resource. It might be my laptop, might be a supercomputer at Argonne, it might be a machine down there in Brazil. And through this cloud-hosted service, I can basically register my function and route it to a particular endpoint. These endpoints, they wrap the Parcel parallel scripting library, which allows the endpoints to dynamically provision resources in different computation environments. It allows them to deploy containers of different flavors and to then execute functions in those containers. And it allows you to support different types of architectures and accelerators. So what else do I have on the slide? So the funcX service, you basically register and share this endpoint. There's a handshake and authentication authorization model there that allows you to pair your endpoint such that only you can use it, or those that you allow to use it can use it. And then similarly with functions, you can register, you can set access control on a function, and then you can run it. And so we term this as being able to turn essentially any machine out there into a function serving endpoint and getting all the sort of benefits of that cloud hosted service sort of for free, right? You're getting the centralized registry of functions. You're getting that reliable 99.9% availability system that you can always speak to, and that system's going to queue your invocations until your endpoint can actually run things. And then you as a user can actually start to pick which endpoint you might want to run things on. So I have probably a dozen funcX endpoints registered. When I've got a given compute or function that I like to run, I can choose, well, do I want to send this to Argonne? Do I want to send it to Nurse? Do I want to send it to my laptop in some situations? So what does this look like if we actually start to drill down into the architecture a little bit? So essentially, when I'm trying to register a machine, it could be an HPC machine here, a Cray running Singularity on the left. It could be my laptop here running Docker on the right. I can deploy these endpoints that are just pieces of Python code. They're basically little Python services that you can pip install, and I'll show you this in a few minutes. You can pip install it, configure it, run your endpoint. You can have multiple endpoints running on a particular machine. At the moment, the endpoint is single user, where a user may deploy it and then share it with other users, not multi-tenant. So individual users basically, or individual collaborations, have to set up their own endpoint and then explicitly share it with the people who are allowed access to it. Each time you deploy one of these endpoints, it gets registered in this funcX registry. And then at some later point in time, a user may come along and register a function. Registering a function is as easy as specifying a Python function and listing the dependencies that go with it. Once you've registered that function, it becomes available in our function registry. We've got some prototype code that's not really out there for common use at the moment that can take this list of dependencies and turn those dependencies into containers that can then be actually sent to machines to run dynamically. At the moment, we ask that people pre-configure containers that they want to run in on the endpoint. And so having registered a function, you or someone else that's allowed to access that function can essentially come along and say, I want to run function 1 with these 10 different input arguments. And that will then get queued up in the funcX system, and it will get dispatched down to the endpoint to run. And the user might come back at some point later and retrieve their results when that function's actually finished. They can also then run another function here, g of x, where they pass in another 5 different arguments. And these things essentially will get queued by each of the endpoints until there's available capacity to run that function. And as I said, it's entirely asynchronous. There's queues at multiple levels here so that we don't lose functions. And so if, say, an endpoint is offline, if a node fails on an HPC machine, if someone closes their laptop, we basically queue that request until that endpoint comes back online, and then we can start executing it again. So how do you deploy a funcX endpoint? So it's actually relatively simple. Essentially, you can pip install funcX, for example, in a Conda environment. You authenticate once, so just to make sure that, that your endpoint is paired to you. So once you've authenticated once, we cache some OAuth refresh tokens on the machine. And so the next time you can basically just use those refresh tokens. And then the final thing you need to do is configure the endpoint for using the local resource. Before the parcel system, which is essentially just a Python config that says, well, if I'm running on a single node, I'm just going to split it up into X number of workers, normally the number of cores you have available, and it will use those. Or if I've got an HPC or cloud system, I need to say I'm using Slurm, I'm using PBS or Cobalt or some other scheduler, and here's how big of an allocation I want to grab. So in this example, you see the nodes per block is 5, and then init, min, and max blocks are essentially scaling parameters to describe how we scale in and out on that HPC resource. And you see at the bottom there, we're saying 28 workers per node, 5 nodes per block. So we've got 5 times 28 concurrent workers that are available to run functions on that machine. And so what does it look like when you now as a user want to actually code against this, to actually write your function and run it? So this looks pretty much just like normal Python, right? So we're basically, the first thing we need to do is authenticate. So this first line, we import our funcX SDK, we create a client, which if you haven't authenticated, we'll ask you to authenticate. We define a function, in this case, a very trivial sum function, just as I said, standard Python function. It can take input arguments, it can return whatever you like. We then register it once. So this is a one-off cost where you register the function, just pass it in. You then pick where you want to run it. So in this case, we've got a tutorial endpoint that anyone can use. I also have my own endpoints that I use for running things. And then when I want to actually run the function, I just call run, I pass in whatever the input is, any args or keyword args that you might have in order. And then at the end, there's a couple of special keyword args here, endpoint ID and function ID, that say which function needs to be run and which endpoint I want to run it on. And then at some point in time later, I can just go and grab the results by calling fxc.getResults. So now I wanted to give you a quick demo of what this actually looks like, and you're welcome to follow along at home. This should, it's always famous last words. This should work for any of you running on the tutorial endpoint. And if you want to set up your own endpoint, it's pretty simple. So this is an HPC machine at Argonne that I'm using called Cooley. Essentially, the first thing I would do is pip install funcX. I've already done that, so I'm not going to do it. The next thing you need to do is basically, when you pip install funcX, you get this funcX endpoint command in your terminal, and so then you can configure an endpoint. So if we call this LIneA endpoint, I configure it. The first time you guys try and do this, it'll prompt you with a little URL to authenticate. That URL uses the Globus Auth system. This doesn't seem to be working. Oh, it did work. It was just very slow. So the first time you'll see a URL pops up, it'll ask you to authenticate. It uses the Globus Auth system, which basically allows you to authenticate with, I don't know, 500 different identity providers, many institutional logins, Google, Orchid, et cetera, you basically just authenticate and say, yes, I give funcX permission to access my identity information, which is just my email and name, and it'll pair that account with you. And then you can do funcX endpoint configure as I did there. And then when I want to start it, all I have to do is do this command, and this will start that endpoint running on this machine. And as I said before, it gives me a UUID. So I should probably have a few. You can see, you can list which endpoints are actually running here. So you see here I have, I don't know what that is, 6 different endpoints running. One of them is the one I just created, this one here. You see several of them are active. 5 out of 6 of them are active at the moment. So I'll just copy and paste this this UUID for that endpoint so we can use it for the actual invocation side. So we have a tutorial notebook here that runs on Binder. So if you're interested in trying this, you can all try this. It's just, it doesn't install anything locally. If you go to funcX.org and click on the Try funcX button, it'll spin up a Binder environment running on the cloud that has all the funcX client dependencies. So you'll be able to run through this yourself. So let me just quickly put this endpoint in here. Okay, I'm just going to put that there. So the first thing I need to do, as I said before, is create a funcX client, and this will show you the authentication piece. See what it's done here. It gives me a unique URL. I go to that URL. It says this is what funcX wants to do. It wants to see my identity. It wants access to global search, which is that provides the registry of endpoints and functions. And then it wants to provide access to funcX so that I can actually call things. And all I have to do is click that. You, of course, if it's your first time logging in, will need to pick your identity provider and authenticate first. Once I've done that, it'll give me a unique authorization code, which I can then paste back in here. And so I do that once. I'm only doing this again because I'm running this on a cloud in Binder that I've never authenticated with before. So the basic usage, if I want to register a hello world function, as I said before, it's just a standard Python function. I register it and I get back a UUID for that function. I can also use a UUID for a function that I've already registered. At the bottom of this notebook, there's some examples of how to search for functions that you've already registered. And then when I want to run it, I just pick the endpoint, as I said before. So we're going to use here the tutorial endpoint, and I'm going to get back I'm going to do run. I'm just going to pass in that I want to run on the tutorial endpoint, and I want to run the function that I just registered. I run this. As I said before, this is asynchronous. So that's now I've handed that off. funcX is off running it. It's got it queued up. It'll send it down to the endpoint. It's going to wait in the queue there until there are resources ready. It'll then run it on the resources, and it will cache the result until I come back and grab it. So at some point later, of course, in this case, I've pre-configured resources, so it'll run immediately. I can come and grab the result. If I want to change this now and say, well, I actually want to run this on the new endpoint I just created, I can just change that parameter, run it again, and now that's actually gone and run on the Cooley cluster at Argonne. As I said before, we can pass in any arguments. So this looks exactly like any old Python function. So if I register a sum function, that's just going to take a list of things and add them up. I register that sum function, and now I define a list of, let me change this so you can see that it actually runs. I'll make that 55. I now pass in this list to the function that I just chose. Let's run this on our endpoint that we just configured. And I'm going to wait here and get the results. You see there, that's 65. I can change this to, if you don't believe that I'm running it, change it to 105. And I can also change this back to the tutorial endpoint and run maybe 1,000 this time and go and run it over there. So you see the idea, the takeaway is that this is very easy for me to basically route things to different places. One caveat of running functions in this way is the functions themselves have to be completely encapsulated. So we need to list every dependency that we have as part of the function. So if I want to rely on a library that I've got, I need to import it inside the function. I need to make sure that that library is available on the endpoint where it's running. So if I want to run a function that just prints date, I do it like this. And I can change this from platform, import platform. This is probably dangerous to live code without thinking about it. I want to get the platform that it's on. I think there's a platform like that. Let's see what happens. No. So this actually highlights one other good thing about funcX is it also serializes up exceptions. So in this case, the way I've called platform is wrong. And so I'm getting back the entire stack trace as if I'd run it locally. So we need to look at, how do we get platform? Platform.platform. Maybe I just need to import platform. Oh. I knew this was dangerous. Let's see what that is. Oh. Okay, let's not go off script. It's too dangerous for us. So the idea, I mean, the takeaway here is that essentially you saw there when I messed it up and I had the wrong way of importing it, I got the exception back. If I knew how to use the Python platform, I would be able to print which actual operating system it was running on, but I don't know how to do it off the top of my head, and me scouring notes or docs is not going to help anyone. So I'm sure those of you at home that are trying along can probably fix that function and actually make it work. You can do other things like call an external application. So if you've got some code written in another language or a script or something, you can just call popen, or you can fork a process that's running there. So in this case, I'm just going to run the echo command, and I should get back hello world as I'm passing in world. If I pass that in, I should get that. Exceptions, as I said before, if I run something that's going to raise an exception, I'm going to get back the entire exception in the stack trace. So you see there, I'm getting back this deterministic failure, which is the exception. The function I defined, as you saw, intentionally just raised an exception. It's the only thing it did. And then if I want to make sort of more interesting applications that probably fit with more of the types of things you guys are thinking about, say Monte Carlo simulation, or run something a million times, I can basically define my function one time. So this is a pretty simple Monte Carlo example that tries to estimate pi by throwing a bunch of points in a box and working out how many of them are actually in the circle. So if I register this pi function, you see here I'm importing the random library. I register it once, and now I can run it. I'm just running it here 3 times. This is just the number of points I'm trying to throw in there. I run it 3 times. I wait for everything to complete, and then I average out the results again. So this will take a little bit longer because this is actually more than just printing hello world. It's actually coming up with a bunch of random numbers and working out how many of them are in the circle. So you see here I ran this 3 times. I get 3 estimates for pi of different degrees of accuracy. I take the average and I get a still fairly imprecise estimate of pi. But of course you could do more. If I did more functions, or if I did a larger number of points in each one, I would get a more accurate representation of pi. I'll leave the rest of this if anyone's interested in looking through it. There's some examples here of how the search index works for functions, how you can register a function with some metadata and then find it. There's some examples here about how you can get information about endpoints you're using, whether or not they're online, how many tasks are currently queued up for running, how many workers are there, what types of resources are available. And then some examples of if you want to run large numbers of functions, it's often inefficient to keep calling the cloud service, so we can batch things up and you can run hundreds of function requests with a single request. Does anyone have any questions on this before I return to slides? Take that as a no. Not even sure if we're configured to ask questions. So for the rest of the talk, I thought I'd jump into some examples of, well, first some illustration of how it's actually implemented, some examples of performance, and then some examples of some early adopters in terms of use cases. So, as I said before, there are 2 main components. There's this cloud service, and then there's the endpoint software that sits there running on a particular resource. The cloud service is basically just a REST web service that's sitting there. It's deployed in Amazon. It can elastically scale to however many people are using it. It exposes a fairly simple API of basically being able to register and invoke functions and register endpoints. Behind the scenes, we use a couple of Amazon services. We use Redis, We use Redis as basically the queue of tasks. So this is where when we get a dispatch request to run a function, we plop it in a Redis queue and leave it there until it can actually be executed. And we use a Postgres RDS instance to store all the less fluid type of things. So all the user information, endpoint information, etc. Underlying these Redis queues, we have a piece of Python code which we call a forwarder. And this forwarder is essentially responsible for being the intermediate piece of code that takes things from the queue and dispatches them to the endpoint for execution. So this forwarder is sitting there, pulling things off the queue and sending them off to the endpoint for actually being executed. So this takes the serialized functions, takes the input arguments, wraps them all up and sends it down. It also handles things like the heartbeats coming from the endpoint, so we know it's online. It manages the response back as well. So it takes things that once they're finished from the endpoint, it takes them back again and then puts them back in another Redis queue to go back to the user. The endpoint, as I said before, the endpoint relies a lot on the parcel library. And so you see here we have up the top, you can see my mouse, we have the cloud service with the forwarders and the Redis queues that we said before. And then at the endpoint, we have this agent that sits here that does things like load balancing, like provisioning resources, like scaling those resources depending on load, and also managing containers that are available. And so this endpoint software basically talks to the scheduler or the local system and deploys a bunch of containers or worker processes to actually run functions. And then it manages basically deserializing that function and the arguments, running it, recording the results, serializing that all back up again and shipping it back over the fence to the web service. We use ZeroMQ extensively for communication, both between the endpoint and the workers, and also between the endpoint and the cloud service. The communication here is all outbound. So most HPC systems are going to limit inbound connections to the endpoint. So the endpoint dials out to the cloud service and says, what jobs have you got for me? Rather than the cloud saying, hey, endpoint, run these jobs. The endpoint, as I said, there's some heartbeat messages that get sent periodically that report the current status. Is it alive? Reports usage, how many things are waiting to be run, et cetera, et cetera. So we've done some fairly extensive performance testing of this thing. We have a paper that was presented at HPDC this year, which is a big high-performance distributed computing conference in our world. And as part of this paper, we did a lot of performance analysis on a couple of supercomputers. So we deployed funcX on ALCF's Theta machine and NERSC's Cori machine. We did a bunch of strong and weak scaling tests. The takeaway points to the left is strong scaling. We basically try and run 100,000 functions as quickly as we can. We try and run the very worst case functions. So no op essentially is running for no time at all. 1 second, a function that runs for 1 second. So of course, with no op, you're seeing entirely overhead of the system. 1 second, you're able to amortize some of that overhead, but you're still just the latencies and the delays of queuing things in the cloud, queuing them on the endpoint, running them on the actual worker. There's a bunch of hops to go through there. So you should interpret this as worst case behavior. If you have longer running functions, things are going to get better. But on the left, you're seeing that we can run reasonably well up to about 2,000 concurrent containers for these very short running tasks. And then we start to level off in performance. So for longer running functions, we'd be further down this line. On the right, we're seeing the weak scaling experiment. So here we're basically increasing the number of workers. And for each worker, we give it 10 tasks and we see how long it runs. In this case, we've also added 1-minute tasks. Which obviously more favorable. And you're seeing here, we see down the bottom, the short running several second or 1 second tasks start to lose performance at 2,000. With the longer running 1 minute ones, we get up to about 20,000. But the big takeaway is here is that we're running on about 100, what are we running on? About 130,000 concurrent workers on Theta with 64 cores per worker. So what's that? Probably 2,000 nodes we're running on here. And we're basically able to run 1.3 million tasks without any significant problems. This figure shows the elastic execution. So one of the big things about this fast function serving model that's sort of attractive is that we can run functions and elastically scale resources based on the workload that's waiting. So this example shows that we've deployed some 1 second, 10 second, and 20 second tasks following this sort of pattern of deployment. And then you're seeing here the resources that are being provisioned in response. So we're seeing the number of, this is running on Kubernetes rather than on HPC. But you're seeing here the number of pods, which is equivalent to a work unit in an HPC system. So you see that as we request tasks, we're provisioning nodes to satisfy the needs of those tasks. And these nodes are being, or pods in this case, are being deprovisioned when we've actually finished the execution. Another thing that we think is really nice about the system is the ability to recover from failures at many different levels. The worker that's actually running on the node that might fail because HPC nodes sometimes fail, the manager that's sitting there managing a pool of workers, and even the endpoint, so the entire laptop going offline or an HPC system being disconnected from the network. So you see in these examples, we've basically just run some workloads here. They're steady workloads, I think, periodically ascending a task that runs for some about a little less than half a second, maybe a quarter of a second. At this point in time, we turn off a manager. So this is like losing an entire node in my system. And you see that right when we turn it off, we're getting some very long latencies because these couple of tasks have been allocated to that manager and they're not able to complete. In this case, we've got a second manager. So the second manager continues to do work. Latencies are getting bigger because there's only one manager now and there's too much work for it to do. But at some point in time, the first manager recovers, and now we start to see that the workload is slowly being executed. On the right, this is showing the entire endpoint. So this is like your HPC system goes offline or your laptop goes offline. When the endpoint's lost, there's nothing we can do. Everything's basically queued until it comes back again. So you see here the latencies are getting periodically shorter as we get closer to the endpoint coming back again. And then the final performance result that we looked at was looking at, well, how can we optimize performance if we start thinking, well, we need to run these for real applications. So we looked at a couple of ways of enhancing performance. The first is prefetching. So essentially an endpoint will ask for more work than it can actually execute. And the second is batching, where we'll actually bundle up as a user or as the funcX service, we'll bundle up a bunch of requests to an endpoint and ship them across as if it's one single request. And so there's obvious positives and negatives of these two approaches. The positive is that you amortize a lot of that cost. You're getting rid of a lot of the overhead because you're bundling everything up together. The negative is you might not get quite as fast performance because you're not able to allocate things as efficiently as you would otherwise. So on the left here, we're seeing the prefetching performance. And you can see here as we increase the prefetch, we're getting a faster average completion time. And you're seeing that once you prefetch at about 50, you get all of the benefit you're going to get. So there's no point prefetching at, say, 250. And this is the average completion time of that task when it's ready to run. So of course, the actual make span, the total time to run all of these things might well be longer because you've sent more things to one node than you otherwise would. On the right, we're showing batching in terms of sending a lot of functions to a large number of workers. And we're computing here the throughput. So if we batch up millions of tasks into individual batches, we can actually get, this is in millions of tasks per second, we can actually get a large number of tasks being pumped through the system. This is running essentially no-op tasks that just complete as soon as possible, just as a baseline, how fast can we actually pump things? And then if we look at, well, what does it actually look like to implement these batch type models on real workloads? So these are some of the example workloads from the first slide where I showed you the runtimes of these things that ran from anywhere from a fraction of a second through to 60 seconds. You're seeing in some cases that you're getting better performance, improved performance as we batch. So the average latency per request is going down. These are the shorter running ones. For the longer running applications, XPCS, neurocartography, and the metadata. Well, metadata is actually short, but it's so short you're seeing all the benefit there. You can't get much shorter than that given the task runs for such a short period of time. But for the two long running workloads, you're not seeing too much benefit of that. We've also started to do some work looking at scheduling. So the student just finished his master's thesis, a student by the name of Rohan, and he looked at, well, can we deploy funcX endpoints on a bunch of different types of machines? So he deployed funcX on 3 Raspberry Pis, he deployed it on an Amazon instance. He deployed it on a desktop in the office when we were allowed in the office. He deployed it on a couple, or three of them actually, a slow one, an average one, and a fast one. He deployed on a couple of mini-core machines and a couple of GPU machines. I think both of them were on the Chameleon cloud. And then he looked at submitting different types of workloads to these, to his meta-scheduling type architecture. And his meta-scheduling architecture would essentially predict how long is it going to take to run this function on a particular type of funcX endpoint, given what it's seen before. Secondly, how long is it going to take to actually ship that function and its necessary data to that endpoint? And third, how long does he expect to wait to get resources based on the queue delay times? And so he ran here 3 different types of applications: a MapReduce application of small, medium, and large, a matrix multiplication application, small, medium, and large, and then a file IO application. And then he looked at 3 different strategies for how to provision these things. And I cut off the bottom one. Oh no, the labels are at the top, sorry. So round robin, which basically just, as it sounds, you send 1 to each node. And of course here you're seeing, this is just representing the fraction of tasks allocated to each type of resource. So you're seeing here that we're, as you would hope, we're getting roughly even number of tasks allocated to each endpoint. So that's nice in terms of sharing the load across the systems, but it's not very efficient in terms of actually running these functions quickly. Second thing he looked at was, well, what happens if I just send a task to the fastest endpoint for running that task? And so in most cases, the MapReduce and the file IO task gets sent to the fastest desktop. The matrix multiplication task gets sent to the GPUs. Everyone else is empty. So you'll get, while these functions are running quickly themselves, they may not necessarily be running fast overall, because obviously you'll need to queue things up a lot when we've got lots of things sent to the same node. And then he looked at a system called smallest ETA, which was his heuristic to try and wrap in all these different features and work out how long things are going to run. And so the nice thing here is you're seeing distribution, and you're seeing distribution of different types of tasks in interesting ways. So where we saw before, the matrix multiplication performs fastest on GPUs. In fact, here, if we take into account the wait time to run these things, it's actually beneficial to send some of them to the Pis that are going to be slow, but eventually they'll outpace the queue delays on the GPUs. And so you start to see this interesting sort of allocation model where we're submitting things to nodes that are most suitable to run those things. So this is very much research work. This is us building a layer on top of funcX and starting to explore some of those ideas of computational fluidity and being able to ship functions to computational or computers or accelerators that are well designed to support that function. So for the last part of this talk, I thought I'd quickly jump into a couple of examples of places where we're seeing funcX being used. The first is this manufacturing and machine learning platform. Most of our initial applications are at Argonne because they're people that we work with frequently, and there's I guess they've been early testers of a system that's been evolving very quickly. So MDML is a machine learning platform that sits there and basically takes data recorded from instruments, runs processing and machine learning inference, and then produces visualizations that help guide the experimenter. So there's a couple here: flame spray pyrolysis at MERF, and then the APS. They basically take data off the instrument as it happens, feeds it into this MDML platform. This MDML platform decides what to run, and then it uses the funcX system to basically run some number of compute tasks on the edge devices. These are like sensors and little computers that actually sit there at the instrument. Some number of functions actually run very close to the instrument on lab computers that are actually sitting there beside it. And then some of them are running on HPC on the Theta supercomputer at Argonne. funcX runs these tasks, returns them back to MDML, that then fills in a visualization dashboard that people use. And this is basically running iteratively over time. A second example is for serial crystallography. And so serial crystallography is a way of imaging crystals like protein structures very quickly, and it does it at room temperature. So they basically have a big, don't know what they call it, an array of samples. They put a bunch of samples in their crystals, and then they fire X-rays through it, image it, and then as a result, somehow magic happens, and they get this map of the crystal structure, which they can then interpret the protein structure. And so they're doing this type of thing for understanding, say, the COVID protein structures. And so what these researchers have done is they've built a whole pipeline of things that runs funcX in various places to do things. So the first thing they do is they're running these experiments. The first thing they're doing is running QA against the experiment, against the acquired data to make sure it's not blurry or whatever. They have a human in the loop step here. So this is all glued together with a workflow where they basically can review it and say yes or no. If it looks all right, then full-on processing happens. So they use Globus to transfer that data to an Argonne supercomputer. They use funcX to then analyze it to run their dials processing applications that we saw earlier. That produces a crystal map that they then visualize. They turn it into a PNG or a GIF. They transfer all of this information back again to the researcher, where they index it in a catalog where they can see it and they can view the results of their experiment and decide what to do with it. They determine, have they got enough data to move on to the next sample? Has something gone inherently wrong? Is there something super interesting here that they need to dig a little bit deeper into? And then the final example is the Data and Learning Hub, which is another system at Argonne. And this is a system that we use to publish and run machine learning models. So you can think of it like a data publication system for machine learning models of various types. You deposit your Keras, your TensorFlow model, you describe some metadata about how it works, what the input data is, and then other people can come along and find that model. And not only can they find it, they can actually they can run it. They can pass in a bunch of input arguments and run inference of that model. So essentially, every model is paired with a container that includes all the dependencies, and then it uses funcX under the covers to route those inference requests to, at the moment, running on a Kubernetes cluster at Argonne, but potentially it could be running anywhere that someone had compute resources. So I'm cognizant of time and wanting to leave a few minutes for questions. So one thing that's sort of interesting about probably the last year or so of playing with funcX and trying to apply it to different use cases is we've learned a thing or two, or we think we've learned a thing or two about where funcX is useful and where it's not useful. And so after talking to a lot of the early users, I think there's some things that came across as real pros, mostly around the complexity and the simplifying the use of different compute resources, being very flexible in terms of adopting these web-based authentication authorization models, making it very easy to move between different machines, making it easy to run. So we're using like Argonne supercomputers here with a backfill queue. So making it very easy to elastically scale and run things on demand rather than having to run your APS experiment where you've collected a bunch of data and then 3 days later analyze it and find out something's gone wrong. We've also found out some places where it's not so useful. So where the ratio of data size to compute is not very reasonable, where there's a lot of data you need to move. Obviously, it makes less sense to ship it somewhere else. Containerization doesn't universally work. It works in most cases, but there are situations where you can't just take a container from one machine and move it to another one. When we're dealing with machines without backfill queues, so you're running on a supercomputer where you can't get around the queue delay, then it can potentially be problematic. But I guess in the same sense, it's also advantageous in that you can choose somewhere else to run it. And then probably the single biggest thing is taking an application that runs and turning it into a bunch of functions isn't always that easy. And we've seen some people just register a Python function that just calls a big suite of Fortran code or C code or something else. And that's fine. But I guess it doesn't quite fit with that whole model of decomposing things into granular functions. I'll skip this slide. This was just to say that funcX builds on the Parcel parallel programming library. There's information about that in parcel-project.org. And I'll conclude with a quick summary here. So we think funcX is sort of interesting because it creates this federated fast ecosystem where you can basically register functions in the cloud, register endpoints with this cloud service, and then you can start routing functions wherever you want to run them. Our initial experiments with users have been encouraging. I think most of the people that have tried funcX in their sites are still using it, which is good. And our scalability analysis and our initial deployment show that at least we can run things to relatively high scale, although we have put some restrictions on the service for now to limit how many tasks people can run concurrently. So you can't submit 1 million tasks in 1 second. We sort of rate limit people so that they spread them out unless they use the batch interface where they don't cause the same sorts of problems. So I should say thank you. DOE funded the initial prototyping work here, and now NSF has stepped in and supported us with a CSSI grant to make this real over the next 3 or 4 years. We welcome collaborations. We welcome anyone here trying it out. We've got an open Slack channel, so feel free to jump on and ask us questions or give it a try. And this is a link to the Binder notebook, as I showed before, that you can step through and run all this on the tutorial endpoint. So thank you again. Any questions?
Hi, Kyle. How are you?
Oh, Louise, I'm good. How are you?
Uh, Trying to survive. But anyway, fantastic. It's pretty amazing what you guys are doing, and it's pretty hard to keep track of all the progress that you guys are making. My question is, of course, is more towards our main interest. I mean, I understand from following what LSST is doing, that they are going more and more towards the cloud. But apparently, this is the model that they are thinking more and more. How does this funcX fits in with their model of running things at the cloud, both at the level of data reduction and also like Joe's sense in terms of science pipelines for the dark age science collaboration? Does that this model fits in?
Yeah, so I think it fits quite nicely in that function serving comes from the cloud world, and it's really an extension of this cloud model to abstract complexity of infrastructure. I mean, in this day and age, should we as scientists really be worrying about low-level hardware, or is that an annoying detail that gets in the way of our science? I think in most cases, it's an annoying detail that gets in the way of the science. So the whole function serving model is 100% cloud. And what this system does is it basically takes you away from that vendor lock-in, so you can actually run these function serving workloads anywhere, rather than say signing up for Amazon and being stuck with Amazon and having to have all your data in Amazon and all your compute in Amazon. This essentially lets you run those same style workloads, but across lots of resources, any resources you might have access to. It might be Amazon Compute Cloud resource, Amazon Elastic Compute Cloud resources, or it might be your HPC center sitting there, a machine that's available to Des or Desk. So we think it's quite compatible. In terms of running workflows and things, funcX sort of came out of one of our biggest challenges with Parcel. And the biggest challenge with Parcel has been, it's all well and good to write these workflows that run with lots of little functions in the Parcel system. And we're doing it a lot in Desk as a way of representing Desk workflows. But the single biggest problem we have tends to be configuring Parcel to run on a new machine. So what we'd like to do is we'd like to make that problem the responsibility of the system administrator, where the system administrator, when they set up their scheduler, they set up their machine, they also give us a Python configuration, a funcX endpoint that's sitting there, that then other users can basically use that endpoint without needing to know anything about the underlying system. And we think that this approach will hopefully make that a lot easier for people. At the moment, we're in a bit of a hybrid where we only have a single tenant endpoint in funcX, so still it's the user deploying it. But in fullness of time, as part of this NSF funding, we want to make that like a Globus endpoint for where you can transfer data in as anyone. We want to make it so anyone can run compute there. Long-winded answer. Sorry, Luis. Did I answer any of your question?
No, you have. And by the way, I remember the last time we were talking with Jim Chiang and so on. I mean, if I remember correctly, Joe was also there. One of the issues was exactly that, how to facilitate the use of NERSC vis-a-vis Argonne and so on. I mean, there was this debate, and apparently you guys have kind of solved this problem. It's basically transparent, the infrastructure.
Yeah, I wouldn't say solved yet, but on our way. So yeah, like one thing we could do now is we could deploy a funcX endpoint on NERSC for all of Desk, and we could share it with a group of everyone on Desk, and they could use that funcX endpoint to run their codes on NERSC without needing to know anything about how Corey is configured. They would just think in terms of a sequence of these little Python functions that need to run.
And I presume Func can be a very complex code, right? I mean, it does not have to be a very simple one.
No, yeah, it can be complete. It can be as complex as you want. So typically, it can be any Python function, and of course can import any modules. So essentially, you can write your own modules that your function relies on, and just make sure they're available on the destination machine on NERSC, for example, and then you can run your function that calls all those external modules.
Can you also imagine a workflow that is built with different endpoints so that different parts of the workflow, even though it's part of the workflow, could be run in different setups just to maximize optimize the operation?
Yeah, so that's one of the things we're most excited about, is being able to sort of, like if you have an application that's got some data analysis that runs well on CPU or runs well on NERSC's, I don't know, does NERSC have KNL? On Argonne's KNL nodes, which are very parallel but very slow, and then you have, say, some machine learning matrix multiplication operation that runs great on GPU. You can ship those two different parts of the application off to two different machines to run them efficiently and then bring the results back together. Yeah, so we want to see more of that. That's exactly the type of scenario that we'd like to enable here, to be able to really optimize that type of execution.
My last question.
Okay.
But you're still stuck with the local scheduler, right? I mean,
yeah.
I mean, in terms of queues and so on, right?
Yeah, so we do use the local scheduler, depending on where we're deployed. So we're deployed in 3 or 4 Kubernetes clusters, and they tend to be quite flexible. But in terms of like the Coreys and the Argons, we use Cobalt and Slurm schedulers. Argon, the ALCF has been very nice to us and given us a backfill queue that basically runs on nodes that are not being used at the moment because they're being held for a big job. So we extensively use them for a lot of our real-time computing. When we have data coming off experiments, we want to run it quickly, then we can use these backfill queues at Argon to spin up nodes very quickly, with the asterisk that they might get taken away from us very quickly as well. But so far that's worked really well for us for online computing.
Kyle, thank you very much for coming again. And I know you're going to be our guest periodically. Okay.
Yeah, I'll have to plan to come back again. You're going to have to. I'm going to keep
today doesn't. Okay.
I thank you very much. Does anyone else have any final questions?
Michelle?
Yeah, all right. If there are no more questions, seeing as we're almost upon the hour, I think we can wrap it up. This Thursday, we'll have Dimitrios Thanaglidis from University of Chicago talking about low surface brightness galaxies in DES. Thank you everyone for coming, and thank you especially Karmative presentation and tutorial.
Yeah, thank you all. Thank you everyone for coming. Thank you for the invite. I really enjoy speaking to you all, and hopefully I'll have a chance to come down and visit sometime soon.
Once the COVID is gone, you're already invited. Okay.
Thank you very. Yeah, I look forward to it. Hopefully any day now, eh?
Okay. Ciao.
Thank you all.
Bye.